All right, welcome back to our fifth class. We finished last time talking about Gauss's law, and we said that with Gauss's law you get some easy problems that just say, hey, what's the flux inside of this closed surface? And you're like, oh yeah, if I just count up how much charge is inside the surface and then divide by this obscure constant, epsilon naught, the permittivity of free space, then that tells me what the net flux is in or out of that surface. So, for example, for this figure here on the image that is not showing up really well at all on the screen, you get zero net flux for that surface because there is as much positive charge as you have negative charge inside that surface. Therefore, you have zero net charge, zero net flux. Another way to visualize it is your flux through a closed surface is going to be related to how many, what the net amount of electric field lines when we draw them out are going to be through the surface. Well, you can see here for this dipole, for every line that comes out of the surface, I have a line coming into the surface. So equal number of lines coming out of the surface to going into the surface tells me that the electric flux through the surface is likely zero in this case. So where I wanted to get to last time, but we ended up doing, answering a lot of questions was, okay, if you look at this figure here, what is the electric flux through the closed surface in the image? And you can barely see it, but maybe you can see it better on your device, but it is this little tan image here. Electric flux, not electric field. We'll have to learn how to calculate electric field. Okay, good. The net electric flux is going to be 1 microcoulomb divided by epsilon naught. You have 6 minus 4 is 2, minus 1 is a total of plus 1 microcoulomb of charge. Therefore, we have net positive flux coming out of this surface here. And I think that's all that we really had remaining. And so now that you've had a moment to sleep on this, before we jump into problems, are there any major questions that I can answer before we dive into any problem sets? Or you're like me when I took this course and it was like, dude, I don't even know what you're talking about. I don't even know what questions to ask. Okay. We're talking about imaginary surfaces now, like, take me back to Physics 1 where there were footballs, like things that I could visualize. And the electrical engineers are like, all right, we're actually starting to get into things that are valuable to me. Any Psych fans in here? The TV show Psych? I think of that. I think of Come On Son. I also think of all the time when I'm eating good food, I'm a fan of delicious flavor. If you haven't watched Psych, I realize it's probably like way old for you youngins in here, but Psych is a great show. I think it was on from like 2008 to 2016. It's good stuff. I got to go meet the cast one time. We won it in a raffle. It was awesome. I was an undergraduate student at Harding, a sophomore, and I skipped all my classes and flew up to New York, and we got to meet the cast. It was great. Don't skip class. I'm a professor now. I can't condone this, but I did it. It was great. Okay. Problem solving. Let's do it. I feel like now that I'm a professor, any lesson that I offer towards my students, it's always like, just don't be a student like me. I was a really bad undergraduate student. I fell asleep in class, most classes my junior and senior year. Not good. A very large, infinite, uniformly charged slab of plastic of thickness 2a occupies a region between the minus a at z plane and the z equals plus a plane. So it's just saying that's what this tan area is showing you. Find the electric field everywhere due to this charge configuration. The charge per unit volume of the plastic is rho. And it specifies this rho, charge density here, if you will, because we said that, okay, if we want to integrate over some charge, dq, then for a volume, that's going to be rho times dv, where I have fallen off the edge of the page there a little bit. So rho times dv. That's going to come in handy here. Now, what we want to consider is when we are looking at this problem, when you want to find what the electric field is using Gauss's law, there needs to be a certain amount of symmetry to allow for you to integrate over a certain region. And that's what this problem is trying to say with this infinite slab. Is just like when we had the infinite sheet last time in class, it means that as I look down at this sheet, maybe the floor beneath my feet, I see floor going out infinitely in every direction underneath me. So what does that tell you about in what direction do we expect the electric field to be pointing in regards to this problem? Top of the screen, bottom of the screen, left, right, out of the screen, into the screen. Some combination of any of those. In what direction do you expect the electric field to be pointing? Yeah, out away from the slab, right? This was the problem that we found last time. We said that for an infinitely thin sheet of charge, which is what we had last time instead of one with some thickness, we said that it's pointed away, and when you're outside of that sheet, the electric field, again, gained in strength, diminished in strength, stayed the same as you got further away from it. Which one was it? Stayed the same. Yes, thank you. So what we should get, and what I'm trying to get you to see, is that regardless of how we calculate the electric field, hopefully under the same conditions, we get the same results, right? Just because we use a different way to calculate something does not mean that we should get a different answer. So what happens is, when we're at this point right here, at the top of, we always call this in physics, or I've always heard it called the pillbox. When you're looking at the top of the pillbox here, we should get that the electric field is going to be one in which you have constant electric field strength regardless of how far away you get from it. It does not drop off as a function of z, the electric field strength. Now, what we're going to find that's a little bit more interesting is you get a different result if you're inside of this tan sheet of charge here, okay? If you're inside of that, you actually get an electric field strength that increases linearly with z. The electric field strength grows as you step further and further away from the xy plane. Intuitively, looking at Gauss's law, no math required, why might you expect that the electric field strength is going to increase as you step away from the origin, so long as you're still inside of this slab here? Ben? More material means more charge that I'm enclosing. So what we're looking at here is we said that Gauss's law states that flux, or that would be the integral of E, the electric field dotted into some area, is equal to the amount of Q enclosed over epsilon naught. Right? That's what we stated. And what I want you to see is the integral over the electric field that we're going to be doing goes as a function of area. But how much charge we've enclosed goes as a function of volume. So I enclose more charge, my volume grows bigger, faster, stronger, like it's the Olympics or something. It grows faster, the volume grows faster than the surface area containing that volume grows. Another way to think about it is, okay, what if you make this pillbox, you shrink this pillbox down to where it's infinitesimally close to the XY plane? What do you expect the electric field to be on the XY plane? 0. Yes, it's 0. You can think of it this way. If you're inside of that tan sheet right there, if somehow you're immersed in it, maybe it's some sort of liquid, right? You're in some sort of bath in space. You have as much material to your right as you do to the left, and it's all positively charged. And electric field lines radiate out away from positive charge. So I have as much electric field strength trying to push down into me from the right, so going this direction, as I do from this material going this direction. Another way to think about that with Gauss's law is if I shrink my pillbox to infinitesimally small, I have enclosed 0 charge. And if I've enclosed 0 charge, then I expect the flux to be 0. And if I expect the flux to be 0, because of symmetry, I expect the electric field there to be 0. So I'm trying to get you to see that all of this complicated integral stuff that we've written down so far can be intimidating to look at. But don't lose the forest for the trees of what we're trying to say with Gauss's law, that electric flux is proportional to how much charge you've enclosed. So if you think through that, it gives you a framework for which you can figure out how to solve problems. And you say, that's easy for you to say. So let's do it together. If I, instead of the way that this is set up currently, if I instead consider a pillbox that is inside of this material right here, say like so, something like this, that's a terrible looking cylindrical area. But I want you to see that I'm inside of the material right now. And the reason that I do that, the first thing I want to consider is how much electric field do we expect to be coming out the walls of this pillbox? The same could be said out here when we're already outside of our material. But if I had this scenario where I'm looking at how much electric field goes out in the row direction here for any of these configurations, what do I expect the component of the electric field through the walls of my cylinder to be? What? Yeah. Let's say that we're not on the XY plane. Anywhere not on the XY plane, what do you expect the electric field in the direction that is always perpendicular to the z-axis to be? 0. Yes, why? Not because it's dead center, but because we have infinite amount of plane going out every direction. We said that the electric field was only pointed in z to begin with. So if the electric field is only pointed in z, we expect that the electric field pointed in rho to always be 0. Right? If we know the electric field points along z, say this direction here, this direction, then rho is perpendicular to z. So if it's only in z, you can't have any component going in rho. So what I'm trying to get you to see is we're only concerned about integrating over this surface area right here. We're integrating over this area right here. We'll call this A. We don't have to integrate over the walls. So what we end up getting is we take this equation right here, Gauss's law, which says that the integral of E dotted into dA, well, as far as I'm concerned, dA, the normal, is parallel to the electric field here. So the dot product is going to be dA in the z hat direction. Those come out to be the integral of E sub z, which we said it would be in anyway, times dA, just from here to here. And then the other side of Gauss's law states that it's Q over epsilon naught. But how much charge have I enclosed at this point? Well, we don't know. We're only given the charge density. So if I want to calculate the charge, then now I have to integrate over the differential amount of charge, dq over epsilon naught, or that would be the integral of rho times the differential volume over epsilon naught. Yes, right here, Bill. Okay, so why is the electric field only in the z direction? Let's consider this infinite sheet of charge, right? It goes this direction. Imagine that it's, actually 2 dimensions, right? But it's going out in every direction equally. And I want to know the electric field at this point P from this point on the sheet. In what direction is the electric field at P due to this point on the sheet? And let's assume the sheet is positively charged. In what direction is it? Down and to the right, right? So let me move my P here. I get that the electric field is going to be along the line radiating away from that point. So I get that the electric field is down to the right. So it's going in the z direction, right? But then we also have, let's call this maybe the y direction. We have some of the electric field going in the y direction. So how do I state that y component there ends up going away? Somebody. Yes, Will. Because no matter what point I choose on the plane, let's call this point 1 on the plane, I can choose a point 2 on the plane down here such that I get this, and the electric field at that one is going to be in this direction, up and to the right. And if I add those two vectors together, then what I get is the net electric field here is going to be only along the z direction. I can do that for any point in space, and I can do that for any pair of points on the plane. Okay? Any other questions before we move on? Yes?
Can you explain a little better what rho dV actually?
Yes. So anytime we have a charge, but it's spread out over a density, you can think of that as an integral over the differential amount of charge where the charge is stored, right? So I have a big region of charge. And if I integrate over this part of the charge and this part of the charge, that whole space, I'm integrating over each individual tiny, infinitesimally small contribution of charge. And we're told in this problem that each individual small part of charge is equal to a volume charge density times a differential region of volume. So what I'm saying instead is, I know rho is constant in this problem. Now what I'm doing is, you imagine an infinitesimally small cube in space. how much charge is stored in that volume is rho. What? Yes. I'm saying what you get is if this is my, let's call this my region with charge density rho. Well, if I have a density of anything, and let's call this right here dV, right? Then my charge density times this region of space, this right here, is my differential amount of charge stored in that space. And if I integrate over either one of these, that gets me the total charge enclosed by the volume, which is what I was told to find according to Gauss's law anyway. Okay. So let's get rid of that. My beautiful drawings. So sad. I saw a quote the other day. It was about the relationship between physics and art, and it was, I tried to be an art major, but I only had the art skills of a physicist, so I chose to be a physicist instead. Thought, yes, that's true. That works for me. Okay, so now what I want to do is take these two integrals right here, and I've got the integral over e sub z times dA equals the integral of rho dV over epsilon naught. And I told you guys back 2 class periods ago that dV in cylindrical coordinates is polar radius, I'll call it r sub p, times dr times d theta dz. I think I used rho, but since we're already using rho for a charge density, I want you to know that this is a linear, I'm not talking about the charge density here, I'm talking about the polar radius. And I also said dA in the z direction here, dA is going to be equal to the polar radius times dr d theta. Okay? Yes, Bill? Okay, why am I using polar coordinates instead of x, y, and z? The general reason is just one for symmetrical simplicity, right? So I could do it this way instead, where I had some sort of cube in here that I was trying to integrate over, like so. And with this, I only had to say that E sub rho, any perpendicular component of the electric field, perpendicular with respect to the z direction, that's 0. So I only had to argue that one orthogonal component was 0. Whereas with this, I'd have to argue that the x component and the y component are both 0. So it's just a matter of simplicity on things that I'm having to drop out of my equation due to symmetry. Now, the reason that I'm doing this is because I know most of you have not taken Cal 3 yet, and so you're not comfortable with taking double integrals, because what we'd have to consider is that this is E sub z times the polar radius times dr times d theta, where dr is going to be, let's say we integrate from 0 to some radius a. Let's call this the radius a right here. And I'm integrating theta from 0 to 2 pi, which is 360 degrees. But then I've got on the right-hand side, I've got rho over epsilon naught. Both those are constants, so let's pull those out. I've got r sub p dr d theta dz. And I guess I need to move that over so I can write this as a triple integral. And you're like, I haven't even made it to Cal 3. One integral is bad enough. What are you doing to us? And let's say I'm integrating from minus z to plus z here. So I'm integrating from minus z to plus z. And my limits of integration on on r and theta are the same because we're talking about Q enclosed. So I have my integral over the surface here, and then I've got the integral of the volume enclosed by the surface. So my limits of integration have to be the same for things that show up on both sides. And this is where, if you take electromagnetic theory 1 and 2, these problems can get very difficult because rho need not be constant. And you have other things that need not be constant. But because everything else in this equation is constant, this actually turns out to be quite simple in terms of what you calculate. Because I get, since all of the integrand is constant with respect to the integrating variables, these two integrals over r dr d theta cancel out. And what I'm left with is instead E sub z is equal to rho over epsilon naught times the integral from minus z to z dz. Or that's equal to rho over epsilon naught times z evaluated at minus z and plus z. Or that's equal to 2 rho z over epsilon naught. Something here. Okay. I didn't miss out on, I messed up on something, but let's pause there for a second. I'm off by a factor of 2 here. I have my electric field strength as double what it needs to be. Can anybody help me explain why I might have that my electric field strength is double what it actually ends up being? Let me go back up to my figure here really quickly. Yes? It actually does not have to do with the thickness being 2A. That's a good guess, though. That was a really good guess. Yes, Bill? Yes, absolutely. So I assumed that all of the electric field strength, the way that I set this up, was coming out of the right-hand side of this pillbox, whereas part of it is coming out the bottom of the pillbox, right? And due to symmetry, I expect half of it to be going out to the right and half of it to be going out to the left. Or I could have done it over, let's call this the integral of the right-hand side. Plus, I'd have the exact same thing where I'd have the integral over the left-hand side of EZ dA. But dA is going to be the same. Though, since they're the same, that's the same as taking the integral twice. So I need a factor of 2 out here, and I need a factor of 2 out here, And those two then cancel. And I get that the integral gives e sub z equals rho z over epsilon naught, or e as an integral is rho times z vector over epsilon naught. Yes? Set negative z equal to 0. Yeah, we could have set up our pillbox to have one face in the xy plane. And then we would only be integrating over, we know that there's 0, we already argued that there was 0 flux through the xy plane. So we would only have to integrate over the right face, and that would be an integral over z from 0 to plus z. So we would have gotten the same result if we had done it that way. Good. Just, I feel like sometimes as a professor I channel Darth Sidious. I might tell you to use your aggressive nature if you get mad at a physics problem or something. Let the hate flow through you. Use it to fuel your energy in solving physics problems. I'll let you guys in your time see my solution on Canvas for the pillbox that is outside, where we get the exact same result as last time, but since we've already seen that result, let's move on. Let's do this one right here. Find the electric field everywhere for a uniformly charged sphere that has a radius r and a total charge q that is uniformly distributed throughout the volume of a sphere that has a charge density rho is q over the volume, where v is 4/3 pi r cubed as the radius. And don't forget, I said to you, if you want a purely geometrical rationale without the integrals, these are all example problems in your book. And so if you want to see just how to think about these things from a purely geometrical standpoint, you can look there. But the purely geometrical rationale only works when rho is constant and when there is definite symmetry. So I get here that, according to Gauss, the integral of E dotted into dA is equal to the integral of rho dV, and that's just equal to the integral. No, let's not do that. Let's just stop there for a second. Well, over the surface of a closed sphere, we said, first off, the coordinate system for a sphere has a polar angle, so one that comes down from the z-axis, whose bounds are 0 when the radius lies on the z-axis, and pi, or if you're an engineer, 180 degrees, when it's on the minus z-axis, so it's bound between 0 and pi, 0 and 180 degrees. Then you've got the azimuthal angle is the one that lies in the xy plane, and it goes all the way around the z-axis, so it goes from 0 to 2 pi, or 0 to 360. But I'm not taking any sort of cut out of this sphere. I don't expect anything to be coming out along the azimuthal direction in terms of electric field, nor do I expect anything to be going out along the polar direction. I only expect, again, by symmetry, that if this is my coordinate system here, let's call this Z, let's call this Y, and let's call this X. By the same rationale of talking with Bill on the last problem, where we expect that all other components of the electric field other than Z cancel out, we can say the same thing here. You can grab different regions inside of the sphere here. Let's say this one and this one. And we expect that the electric fields due to each one of those are going to end up canceling out to where the electric field is only going to lie in the radial direction. So this would be the radial direction right here, R. Now let's pause for a moment and let me tell you a place that students tend to mess up when we do problems such as these, because we're going to do one after we talk about conductors here in just a second. We're going to talk about slightly more complicated problems where you have layers of charge density. You got to figure out what the electric field is due to each subsequent layer of spherical shell, E. Students tend to think about this when they do their limits of integration of, okay, I'm integrating 0 to R, where R is, say, the radius of where the charge exists. But that's not true. What Gauss's law states is when you have some sort of closed surface, we're looking at how much charge is enclosed by the surface. And so what you're integrating over is not the spherical boundaries necessarily of your charge, but you're integrating over the imaginary surface that you're working with at that time. So in this case, let's call this radius of the blue sphere, they call it just magnitude R. We would be integrating our electric field over this region rather than this one alone. Okay? So let's do this problem first of all when we have our spherical shell inside of actually, I guess what we're doing here is, they've already got it drawn. We're doing this one first, part B. Yes, Ben? It is similar to integrating an arc length if your arc length was closed in on itself, like a circle or a square or something like that. But then you bump that out into 2 dimensions, so we're integrating over an entire closed surface instead of a single closed contour. So yes, they're similar, but not the exact same. Not multiply by 2, multiply by 1 extra spatial dimension. Okay. So I get dV for a sphere is r squared sine theta. I'm going to run out of room again. Maybe I should just zoom out a little bit. Nothing like making it harder to see because you zoom out, right? Times dr d theta d phi. And we said dA in the radial direction was equal to r squared sine theta d theta d phi. Like, how do you know that off the top of your head? Many, many years of teaching this. You don't set out to memorize things. You just do it enough and it happens anyway. Why do you think I give you homework? Right? Because I'm mean. But beyond that, because I want you to learn. Practice makes perfect. Okay. So my integrals become e sub r times r squared sine theta, oops, not sine squared theta, d theta d phi, where again theta goes from 0 to pi, and phi goes from 0 to 2 pi. And rho dv, so in this case, rho is a constant. dv is r squared sine theta dr d theta d phi. Bless you. And again, we've got that due to symmetry, we get these two integrals here. So this would be, let me move this one out, dr. So that would be theta goes from 0 to pi, phi goes from 0 to 2 pi, and r goes from 0 to r. Since my integrands are both constant with respect to theta and phi, we can make the same argument we did last time and say that, okay, in that case, we expect these portions here to go away, and we're left with E sub r is equal to rho times the integral from 0 to r dr. Or that's just equal to rho times r. So taking big, scary integrals, seeing symmetry and allowing that to save us time on calculating those integrals, and we get pretty nice results. Yes, Andrew? Theta is the polar angle. Yeah, theta is the polar angle. And what we might do instead, because they give us here that rho is equal to Q over V, so that's going to be equal to, let's see here, E sub r is equal to Q over the total volume times r. And that's equal to Q divided by 4/3 pi big R cubed times R. That's equal to 3QR over 4 pi R cubed. So just like we had before, we get come on. Let me just show you what I'm saying, oh, come on about. Thank you, Google, for signing me out of my Google Drive account during the middle of class. Infinite wisdom and security. I haven't gone anywhere. It's not like anybody's taken my stuff. So frustrating. Come on. Who wants to use Adobe? That's Adobe. As you might be able to tell, I'm more than a little bit frustrated here. Yeah, I think my solution, I ended up leaving something off there. Trying to think if I ended up I found where my mistake is. Okay, never mind. Let's do it this way instead. I think where it doesn't work out quite as nicely is from this, if we were to do the integral, you get E sub r times the surface area of a sphere, which is 4 pi r squared, is equal to rho times the volume of this sphere, which is 4/3 pi r cubed. There it is. I had some terms that weren't canceling out the way they were supposed to. 4 and 4 cancel out, pi and pi cancel out, r squared and r cancel out. So that's where I only have a factor of 3 in the denominator. So I've got, this is E sub r equals 1/3 rho r. Yeah. And then 1/3 rho r, I get, trying to see where everything cancels, sorry. One-third rho r, but that's equal to q over 4/3 pi r cubed times r. But now I'm still not getting those cancel out. I'm still a factor of 4 off from what I had before. It's q r over 4 pi r cubed. I think there's a mistake on my solution here. 4 pi and 4 pi cancel. Yeah, there's a mistake on my solution. It's off by a factor of 4. And I'm also missing one other thing in this solution. Does anybody see what it is? Yeah, I missed epsilon naught at the beginning. I've got divided by epsilon naught all the way through this. So that means that there's also additional factor of epsilon naught here, epsilon naught here, epsilon naught. Yeah, and this, my solution is wrong on Canvas. I'll try to fix that. It's off by a factor of 4. I just left it out on my final solution. Sorry about that. If any of you ever become teachers, I never get more nervous when I mess up a solution during the middle of class. Okay? Now, if this sphere, if we went back and did part A, does anybody have any intuition about what the correct answer would be if we go back and do part A? Do you expect the electric field to stay the same as you get further away from the charge? Do you expect it to drop as you get further away? Do you expect it to increase as you get further away? What do you get? It drops off, yes. Does it drop off by a factor of r, square root r, r squared? It's going to drop off as a function of r squared, right? Because as far as we're concerned, after we've left the confines of this sphere, we can imagine that all of that charge was shrunk down to a single point, right? Because Gauss's law states that, okay, we've got this problem right here. While I'm outside, I've got my integrating sphere looks something like this. Imagine that was a sphere instead of a circle. And whether my charge density looked something like, let's see if this shows up, something like, that's terrible. This, where I'm integrating over this charge density. Like so. This should be the same as if I integrate instead. How do I paste? This should be the same as if I integrate over, come on. This is so frustrating. This right here. That's Q, and the total charge on this guy is Q. Right? Those are the same. I have enclosed the same amount of charge. I'm looking at a blue circle with the same radius. And so what I expect to get is instead I've got my integral is E sub r times r squared sine theta d theta d phi equals Q enclosed over epsilon naught. But I'm given that charge Q, and when my integrating sphere is outside of the charge density, I've enclosed the entirety of Q, right? And I have my factor of epsilon naught there. If you integrate over this, since E sub r is independent of, and r, I should say E sub r and r are independent of theta and phi, it essentially becomes E sub r times r squared, or I should say times the surface area of a sphere. So that's E sub r times 4 pi r squared equals Q over epsilon naught, or E sub r is equal to 1 over 4 pi epsilon naught times Q over r squared. And you said, but you told us that this should be the same electric field strength as for a point charge. But it's not. What did we say was the electric field strength of a point charge, some radius r away from that point charge? KQ over r squared. But K is defined as 1 over 4 pi epsilon naught. So that's K. So that tells me that what we get is KQ over r squared. When you're outside of a spherical charge density, you could imagine that that spherical charge density is the exact same as if you collapse that charge down to a single point. Okay? So part A was actually quite trivial. Part B, less so. Any questions about either of these solutions before we look at a few slides and talk about, okay, what if instead of uniform charge densities, what if instead this is over some conductor? Yes, Andrew. Little r represents the radius of my integrating surface. That right there. Big R is the radius of the shell, yes. Right there. You can barely see it, but that would be that right there.
Why is it that when little r equals big R, you get a point charge formula?
When little r equals big R, so when you're at the boundary, right? Take a look at these two results right here. And in both cases, let little r go to big R. What happens? They're the same. Yes, you have met the boundary condition that regardless of our two solutions, since they both work at the boundary, we get the same result. So at that point, if I am at the boundary, I've enclosed all the charge, it still behaves like a point charge.
That's just coincidence. If you continue to expand little r, then it doesn't reflect that anymore.
If you continue to expand little r, it does reflect the fact that the charge density still looks like it could be a point charge at the origin.
If you set the limit to say r goes to double, little r goes to double r, you would end up with
Right, there is no big R in the solution where R is less than little r. Big R is less than little r. So there are no big terms here. You let that go. It just tells me that my electric field strength would be 1/4 the amount that it is at the boundary here of this charge density. Any other questions? Is the back of your laptop, are those Greek letters? It's not? It looks like lambda, sigma, something. Okay. I was going to say, I don't know of any laptop company that has Greek as their laptop logo or their company logo. I should start one. Yeah. I'll just choose the easiest one, alpha, beta, gamma, delta. We'll just go with that. Abgada, for those of you who need the English transliteration of that. Okay. I've built desktops. I've never built a laptop. I hear it's much harder. Okay. Let's talk about how conductors work. And until we do so, with the 22 minutes remaining, because we've been doing integrals, we'll take a bit of a brain break. Yeah. If you ever become teachers, may Google never sign you out of your account during the middle of class when you depend on Google Drive for everything. Super duper smart. That would be super duper helpful for this class. Sigma. Oh my. Come on, guys. Y'all are college students, not like middle schoolers. Come on. Infinite food? But does that also come with infinite, like, calorie burning? So that way you don't gain infinite weight? Be green, I guess. But does that come with being the Hulk? Or do you want to just be green? Or are you saying you want to be all things green energy? Teleportation, infinite booze. Your blood alcohol count would be fatal if it were infinite booze. I'm sorry. What? Your blood is just alcohol. You're in an infinite state of buzzed. Maybe that's what Buzz Lightyear was. I mean, what he calls him, Mr. Lightbeer. I don't know. Dolphin powers? Is that are we talking like Minecraft when you swim and you get dolphin powers? Or just like the ability to speak like a dolphin? Shape-shifting, parallelized minds. Oh my goodness. Too many memes on here. Bless your hearts. Okay, so we've talked about uniform charges and charge densities and all that other stuff. But now we have to consider, how about conductors? What about conductors do we expect to be different here? And electrical engineers, you may already have some sort of intuition about this, even though we might not have formally stated it yet here in this class. We've seen for a couple problems to date, like the infinite sheet, this is what's shown in the image, where the electric field can be discontinuous. We saw in the last problem where the electric field was continuous at the boundary. But the electric field can be discontinuous. And this is important because this is exactly what's going to show up in the case of conductors. The characteristic of electric field near conductors and electrostatic equilibrium tend to create discontinuous electric fields. Yay! It's cool though, right? I mean, because otherwise conductors wouldn't really be conductors, and we'll see that why here in a second. For a conductor in electrostatic equilibrium, the charge distribution, that is, the fields, are not changing. Any excess charge lies on the conductor's surface. And I said next slide, but let's just talk about it here. Why do you expect excess charge to lie on the surface of a conductor? So it's easily transferable because conductors do like to share their charge. Okay? Let's assume that the conductor is isolated in space. You have a single conductor on it, and I drop 1 nanocoulomb of charge on it. That charge then pushes to the surface. Why does it push to the surface? First off, yeah, go ahead. Yes, charge is allowed to move infinite. In a perfect conductor, we can move charge without any constraint. We can move it anywhere, right? Or you could say that because the electrons are not bound to any particular atom, I can move those electrons anywhere freely inside the material. So you have a solid metal sphere, a solid conducting sphere. And I don't know why I'm getting feedback here. I'll move back down. I drop 1 nanocoulomb in some arbitrary location inside the sphere. Those electrons, or lack of electrons in that regard, let's say it's negative 1 nanocoulomb, so I'm dropping in excess electrons. Those things repel each other and move as far away from each other as they can. And then they spread out evenly over the surface, because then their surface repulsion is going to be equal. I want to say that for every electron that I've got here repelling me, I've got to have one behind me, and one to the left, and one to the right, and one this direction. So they spread out evenly over the surface. So then I drop an additional 1 single electron into some arbitrary space inside of that conducting sphere. Well, let's say if the conducting sphere is here, should have brought in my lacrosse ball. The conducting sphere is here, and I drop it closer to the left-hand side of the sphere. It is closer to more charge over here on this side, and so it ends up moving away, and it is unstable at the origin, so it doesn't go to the origin. It moves until it finds a spot on the surface, and the surface charge density then redistributes itself. Essentially, what's happening is when we have a non-uniform, or not non-uniform, when we don't have the electric field over the surface distributed evenly, you end up getting an electric field inside the conductor. But what happens, here's a really good question, electrical engineers. What happens if an electric field exists inside of a conductor? What? Charge moves. Yes. If an electric field exists inside of a conductor, Charges are accelerated by electric fields, and they're allowed to freely do so inside of a conductor, so the charge moves. And so the electric field exists, charge moves to counterbalance that, making in electrostatics, making the electric field go back to zero. Right? As long as there is non-zero electric field inside the conductor, the charges are going to move inside the conductor to try to make the electric field zero inside the conductor. They continue moving until the electric field goes to zero inside a conductor. But then you think, okay, there are ways to maintain an electric field inside of a conductor. Say you put a voltage across that conductor. That makes it where you maintain an electric field inside the conductor, meaning you're continually moving charge one direction along the conductor. We call that direct current. Right? But right now, we're just talking about electrostatics. Things are allowed to come to equilibrium. So what we expect is that the electric field is going to go to zero. If the field, maybe said a little bit more succinctly, if the field inside a conductor is non-zero, then charge will be accelerated by the field. When the charge distribution on the conductor or the field in the conductor is perturbed, charge is moved in an instant in response to the change. Since inside of a conductor, the charge can move freely. This change occurs such that the change in field is negated by local Coulomb effect of each moved charge in the conductor. Suffice it to say, if that is a whole bunch of verbal jargon in your opinion and you don't follow what's going on, what I want you to understand more than anything else is that the electric field inside of a conductor in electrostatics is zero. The electric field inside a conductor in electrostatics is zero. And by extension of that, all excess charge is going to exist on a surface of that sphere, of that object. It doesn't even have to be a sphere. Let's just talk about any arbitrary conductor. The charges move to the surface. Skin effect. I'm racking my notes from electromagnetic theory because I know that comes up. But as far as I know, and tell me if you're talking about something else, when I talk about skin effect, I'm talking about when an electromagnetic radiation is incident on a conductor, right? And so the skin effect is how, it's a depth as to how quickly you expect the electric field to be diminished inside the conductor, or the electromagnetic field. In that case, it is related and it is due to these factors here, but as you would expect, since we're talking about AC, one, it's not in static equilibrium at that point, and it's not a constant electric field, it's a constantly changing electric field. So it is akin to this effect with added complication. As a physicist, I try my best to forget that there is such thing as AC power at all, and I try to just think about, and it's easy as an astrophysicist, right? Because all current is a movement of charge, and generally what happens in deep space is you have a cloud of ionized gas, and it's just moving in one direction, so it's pseudo DC current in deep space. Maybe that's overcomplicating it for you. Yes, Andrew?
If all of the excess charge lies on the outside conductor, you replace the charge in the center of that conductor. Wouldn't the outside charges just hold that one charge?
It's an unstable equilibrium. So in a classical case, yes, it is an equilibrium and it would stay there. But we also have to consider that there are quantum effects, and that thing isn't going to just sit still inside the origin. And the moment that it moves one direction, it gets pushed out into some other, towards the exterior of the conductor.
Wouldn't that then be counteracted though by pushing, it would just gain a velocity for every time it, say, jumps, right? It jumps to a location, say, a centimeter away. Would that then translate to velocity and just gain an oscillation?
But you have to think, too, that the charges on the surface are going to change in response to this one moving as well. The charge on the surface isn't all going to sit still. They move as well. And because they move, you end up losing the symmetry in your electric field. Good question, though. Really good question. That almost stumped me. That was one class that I had. One classical mechanics class, so juniors and seniors at Harding, their goal every day was to ask me a question that would stump me. That was in some ways fun and in some ways frustrating. Okay, we've already stated this, but if the field is inside the conductor is zero, then by Gauss's law there cannot be any net charge inside the conductor. Inside the walls of the conductor. Let me be abundantly clear about that. The main takeaway, again, if you get nothing else from these slides, the electric field and net charge within the conductor in electrostatic equilibrium is zero. Electric field and net charge within the conductor in electrostatic equilibrium is zero. Ahoo! Ring. Okay. Let's looky here then. Let's actually come back to this problem and look at instead, I want to look at instead this problem right here. Consider the solid conducting sphere and concentric conducting spherical shell. The spherical shell has a charge of -7Q. The solid sphere has a charge of +2Q. How much charge is on the outer surface and how much charge is on the inner surface of the spherical shell? So we want to know what is Q out here and what is Q in. And I will tell you, when I ask a similar question on the first exam or the final exam, the majority of you tend to say that the charge on the inner wall there is 0Q, and the charge on the outer wall is -7Q. But we just said that charge has to lie on the surface, not that it has to lie on the outer surface. It just has to lie on a surface. So how in the world do we calculate how much charge is on the inner and outer wall of this shell, respectively? What can we use? What tool set can we use that we have learned to date, Andrew, to help us solve this problem? It is Gauss's law. Okay, if I use it first over the outside, the only thing that's going to tell me, you're on the right track though, so I'm not trying to pick on you. The only thing that tells me is that the net charge inside of that sphere, the total charge inside of that sphere, should be -5Q, right? It doesn't tell me necessarily where that -5Q exists, but just that I have to have -5Q inside of that sphere. You're a hair away from where we need to be. If we do the flux anywhere inside of this right here, so I'm going to do my integrating surface is going to be right here, anywhere between the inner and outer wall of the shell. We said that Gauss's law states that the flux is equal to the Q enclosed divided by epsilon naught. Right? What is the electric flux through that black circle that I've drawn here? I guess, I don't know why I made that sound like I had more to say. What is the electric flux through that black circle that I have drawn here? I mean, according to Gauss's law, if I want to calculate electric flux, then I've got to do the integral of E dotted into the surface area of this black sphere here. What is that flux? This comes into the things that we just talked about 10 minutes ago. I think I heard somebody say it. The electric flux inside of that sphere is 0. Why? Because what? It's not the surface. I'm inside of the walls of the spherical shell. And as I have been told, as we just talked about, the electric field inside of a conductor in equilibrium is 0. If the field is 0, I don't know why I was pointing with my finger, you can't see that. If the field is 0, I can integrate over however big of an area that I want to, but the integral over an integrand of 0 is always 0. So, the net flux is equal to Q enclosed over epsilon naught. Or, I have that 0 is equal to the net charge enclosed by where the charge can exist. And I've got plus 2Q here, so that's equal to plus 2Q plus Q on the inner wall is equal to 0. So that means Q on the inner wall is equal to minus 2Q. Right? If the net charge has to be 0 because there is 0 net flux inside the wall of the conductor, because there is 0 electric field inside the conductor, then that means if there is plus 2Q on the inner solid sphere, I have to have minus 2Q distributed evenly over the inner wall of the shell. So how much charge is on the outer wall of the shell? -5. So it ends up that you were right, but we just had to reason why it was there to begin with. Q on the outer wall of the shell is equal to minus 5Q. And you say, well, how did you know that? Well, it's because Q on the inner wall of the shell plus Q on the outer wall of the shell has to be equal to minus 7Q, because that's what's given up here to us in the problem. And so that requires me that minus 2Q plus Q out is equal to minus 7Q, or Q out is equal to minus 5Q, which is exactly what we've got here. We'll pick up there and work on calculating the electric field next, but otherwise, y'all have a great day. I'll see you on Tuesday.
See you later, Lizette.